Somewhere in a distant galaxy, a massive star is spinning itself to death. It has been burning for millions of years, building pressure, fusing heavier and heavier elements in its core. But unlike most stars, this one will not fade quietly. When it dies, it will collapse inward, then explode outward with a force so extreme it will briefly outshine entire galaxies. In that instant, twin beams of radiation will erupt from its poles, focused, narrow, and unimaginably powerful. If one of those beams were aimed at Earth from close enough range, our atmosphere would begin to unravel. Satellites would fail, ozone would collapse, life on the surface would be exposed to lethal radiation in minutes. This is not theoretical. These explosions are real. They are called hypernovas. They are among the most violent events the universe can produce, releasing more energy in seconds than our sun will generate in its entire lifetime. If you're fascinated by the extreme edge of cosmic reality, the events that shape galaxies and decide the fate of worlds, subscribe now. This channel exists to explore exactly that. Tonight we're going to explore what a hypernova truly is, how it forms, why it's so powerful, and what would actually happen if one occurred too close to us. Because somewhere, right now, a star is spinning faster than it should, and when it dies, the universe will barely notice. But if we were nearby, we would never know what hit us. The invisible chains, the strong nuclear force. Begin with the smallest scale imaginable. Smaller than atoms, smaller than protons, smaller than anything you could place under a microscope or detect with the naked eye. Inside the nucleus of every single atom in your body, something remarkable is happening. Protons are crammed together in an impossibly tight space, each one carrying a positive electrical charge. Basic physics demands that like charges repel each other, and the repulsion between protons packed at nuclear distances would be enormous. By every ordinary measure of nature, atomic nuclei should not exist. They should explode in the first instant of their formation, scattering their contents across empty space. They do not, and the reason is the strongest force nature has ever produced. The strong nuclear force binds quarks, the fundamental particles that make up protons and neutrons, through particles called gluons. Think of gluons as ultra-short-range cables of pure force, lashing quarks together in an arrangement so stable it can survive billions of years without loosening. The force they carry is roughly 137 times more powerful than electromagnetism at close range, and an almost incomprehensible 100 trillion times more powerful than gravity. To frame that comparison differently, if you imagine gravity as the faint glow of a birthday candle, the strong nuclear force would be the surface of the sun at noon. They are not even in the same category. What makes this force particularly strange is its behavior under stress. Most forces in nature diminish as objects separate. Gravity and electromagnetism both weaken rapidly with distance. The strong force does the opposite. The harder you try to pull two quarks apart, the more powerfully they resist. Scientists call this property confinement, and it means that isolated quarks simply cannot exist in normal conditions. Attempt to separate two quarks and you pour so much energy into the system that the force field spontaneously creates new quark pairs from the vacuum itself. You end up with more bound quarks, not free ones. Nature refuses to let them go. This behavior operates at scales so small that the word small fails to capture them. The strong force acts across distances measured in femtometers, 1/4,000,000th of a meter. At these scales, ordinary concepts like location and velocity dissolve into probabilities. Space and time flicker with quantum uncertainty. The universe at this resolution looks nothing like the one we inhabit at human scales. Yet for all its ferocity, the strong force has a strict boundary. Step even a tiny fraction beyond the edge of an atomic nucleus, a distance roughly 1/10,000,000th the width of a human hair, and the force vanishes entirely. Its power is absolute within its domain, and invisible beyond it. Without this force, the periodic table would consist of one entry, hydrogen. Every element heavier than that, the oxygen you breathe, the carbon in your cells, the iron your blood carries, would be impossible. Stars could not fuse elements together. The universe would be a thin, cold gas of unbound particles drifting in permanent darkness. The strong force does not simply exist in nature. It is the reason nature exists at all. The brightest fires. Gamma ray bursts. Now expand your perspective by a factor of roughly 10 to the 30th power. Step back from the quantum realm and look out across the cosmos, where the most luminous explosions in the observable universe are detonating with staggering frequency. Somewhere in the universe right now, a massive star is dying. Not quietly, not gently. It is collapsing inward with a gravitational force that crushes its core to nuclear density in under a second, then launches the consequences of that collapse outward in a beam of energy so concentrated and so ferocious that it briefly outshines everything else in the observable universe combined. This is a gamma ray burst, and it is by most measures the single most violent event that can occur in the present-day cosmos. The stars that produce these events are the extreme outliers of stellar physics, behemoths containing anywhere from 20 to 100 times the mass of our Sun, burning through their hydrogen reserves so rapidly that their entire main sequence lifetime lasts only a few million years. Our own Sun has been burning for 4.6 billion years and has billions more to go. These stellar giants live and die in a fraction of that time. When their nuclear fuel runs out, the core collapses almost instantaneously. The outer layers, no longer supported by the outward pressure of fusion, begin to fall inward. But if the star was rotating rapidly at the time of death, something extraordinary happens. The infalling material cannot collapse symmetrically. Instead, it forms a swirling disk of superheated plasma around the newly born black hole at the star's center. The intense magnetic fields generated by this disk twist and coil until they snap, and in doing so they launch two opposing jets of plasma outward from the black hole's poles at velocities approaching 99% the speed of light. Those jets punch through the remaining stellar material and burst into open space as focused beams of gamma radiation. The energy released in a single short gamma-ray burst, sometimes over in as little as 2 seconds, can exceed what our Sun will radiate over its entire 10 billion year lifetime by a factor of several thousand. In October 2022, astronomers detected what has since been dubbed the Boat, the brightest of all time. This single event was so energetically extreme that it overwhelmed gamma-ray detectors positioned throughout the solar system and measurably altered the ionization state of Earth's upper atmosphere. The source was 2 billion light-years away. The next time you try to grasp the scale of 2 billion light-years, remember that a beam originating at that distance still managed to perturb the air above your head. These events are also time capsules. The most distant gamma-ray bursts ever detected carry light that began its journey when the universe was less than 1 billion years old, when the first generation of truly massive stars were just ending their short, violent lives. By studying these ancient signals, astronomers can peer back toward the dawn of cosmic structure, observing a universe more turbulent and more energetically extreme than anything that exists today. And yet, as extraordinary as gamma-ray bursts are, they represent only one expression of the universe's capacity for violence. To find something more fundamentally threatening, something that bends the very architecture of reality, we need to visit the darkest objects in the cosmos, the gravity kings, supermassive black holes. At the center of our own galaxy, approximately 26,000 light-years from where you are right now, sits a body containing 4 million times the mass of our Sun compressed into a region smaller than our solar system. Astronomers call it Sagittarius A star. It is, by any reasonable measure, a terrifying object. It is also among the smallest of its kind. the most massive black holes discovered to date contain the equivalent of tens of billions of solar masses. Ton 618, a black hole powering an ancient quasar, holds roughly 66 billion solar masses within its event horizon. At that scale, the event horizon itself, the point of no return beyond which nothing can escape, is larger than our entire solar system by a significant margin. What makes these objects so difficult to comprehend is not just their mass, but the way that mass distorts the fabric of spacetime around them. General relativity tells us that massive objects curve space, but near the event horizon of a supermassive black hole, that curvature becomes so extreme that the usual distinction between space and time breaks down. Directions that point outward in normal space are redirected toward the singularity. Escape becomes geometrically impossible, not merely energetically costly. Time itself slows near these objects. A clock positioned just outside the event horizon of a supermassive black hole would tick at a rate thousands of times slower than an identical clock positioned far away. This is not a trick of perception or an engineering limitation. It is the actual physical structure of time being warped by mass. The mystery deepens when we ask how these objects formed. The most distant quasars, some of the brightest objects in the universe, powered by matter falling into supermassive black holes, are seen as they existed when the universe was under 1 billion years old, yet the black holes driving those quasars already contained billions of solar masses. Normal stellar evolution, which produces black holes one dying star at a time, cannot explain this. The universe simply had not had enough time to grow such objects through ordinary means. Current theories invoke direct collapse scenarios, where enormous gas clouds in the early universe bypassed the normal star formation process entirely and collapsed directly into massive black hole seeds. These seeds then grew exponentially, merging with other black holes and consuming surrounding matter at rates that push the physical limits of accretion. Whether this explanation is correct remains an open question. What we do know is that supermassive black holes are not passive objects. When they are actively feeding, they become the most luminous, persistent sources of energy in the universe. Matter falling toward the event horizon forms a disk that heats to tens of millions of degrees. The innermost regions of this disk orbit the black hole at a significant fraction of light speed, emitting radiation across the entire electromagnetic spectrum. The resulting quasar can outshine the combined light of every star in its host galaxy by factors of hundreds. And then there are the jets, beams across the cosmos. Relativistic jets. When the conditions around a feeding supermassive black hole align correctly, the right mass, the right spin, the right magnetic field configuration, the system does something almost paradoxical. It takes some of the infalling matter that should disappear forever into the singularity, and instead launches it back out into the universe as a focused beam of plasma moving at 99.9% the speed of light. These relativistic jets are among the most structurally baffling phenomena in astrophysics. They emerge from the chaotic environment of an accretion disk, swirling with magnetized plasma and extreme radiation, and yet they maintain almost perfect collimation across distances that can exceed 1 million light-years. Observed with radio telescopes, they appear as straight, razor-thin lines crossing the sky, threads of focused destruction that somehow remain coherent across intergalactic scales. The energy these jets carry is staggering. A single jet from an active quasar can transport enough power to prevent new star formation across an entire galaxy cluster. The plasma within the jet moves so fast that each individual proton carries millions of times more kinetic energy than the most energetic particles we can produce in the Large Hadron Collider. When these jets eventually slam into the surrounding intergalactic medium, they inflate enormous bubbles of hot plasma that persist for hundreds of millions of years, slowly reshaping the large-scale structure of matter in their vicinity. When a jet points almost directly toward Earth, we observe a special phenomenon known as a blazar. The apparent brightness of the jet is enormously amplified by relativistic beaming, and small variations in the jet, turbulent knots of denser plasma moving through the beam, can cause the observed brightness to swing by factors of hundreds within hours. These same knots appear to cross the sky faster than light, thus an optical illusion created by the geometry of near light speed motion, where the component of velocity directed toward the observer compresses what would be weeks of travel into what appears to be hours. These jets may also be responsible for producing the highest energy cosmic rays, particles that slam into Earth's atmosphere carrying individual energies equivalent to a macroscopic object thrown at ordinary speeds. The accelerating fields within relativistic jets stretch for millions of light years, making them the largest particle accelerators in the universe by an enormous margin. The invisible tide, dark energy. Everything we have examined so far, black holes, gamma-ray bursts, stellar explosions, relativistic jets, operates within the framework of space. All of these phenomena move through the cosmos. They do not alter the cosmos itself. Dark energy does. In the late 1990s, two independent teams of astronomers set out to measure the deceleration of the universe's expansion. They expected to find it slowing down, pulled inward by the collective gravity of all the matter it contains. Instead, they discovered something that earned their work a Nobel Prize and has challenged physics ever since. The expansion of the universe is accelerating. The cosmos is not gradually decelerating under its own gravity. It is flying apart faster and faster, driven by a force that accounts for roughly 68% of the total energy content of the observable universe. That force is dark energy, and almost nothing is understood about what it actually is. What we do know is how it behaves. Unlike gravity, which weakens as objects move apart, dark energy maintains a constant energy density, even as space expands. As the universe grows larger, there is simply more space, and therefore more dark energy. The force driving expansion grows in total magnitude as expansion continues, creating a self-reinforcing cycle with no natural stopping point. The universe is not merely expanding, it is expanding at an accelerating rate that will itself accelerate. The most widely accepted theoretical description treats dark energy as a property of empty space itself, a cosmological constant built into the equations of general relativity. Einstein originally introduced this concept, then abandoned it when the universe was thought to be static. He called it his greatest mistake. It may have been his greatest prediction. The long-term consequences of dark energy rewrite the cosmic calendar. In roughly 2 trillion years, the expansion will have carried all galaxies outside our local group beyond the observable horizon. The night sky will go dark as the light from distant galaxies is stretched to infinite wavelengths before it can reach us. Billions of years beyond that, dark energy may grow strong enough to overcome the gravitational binding of galaxy clusters, then individual galaxies, then solar systems. In the most extreme scenarios, a phase called the Big Rip, the force driving expansion eventually exceeds even the strength of chemical bonds and the strong nuclear force. Planets dissolve, atoms themselves are torn apart. The universe that spent billions of years building complexity through gravity and nuclear fusion ends not in darkness, but in enforced separation. Every particle driven away from every other particle until the cosmos is nothing but an infinite, cold void of isolated fragments. Dark energy may be the gentlest seeming force in the present day and the most devastating force in the long run. Mountains of compressed death, neutron stars and magnetars. Picture the mass of our entire sun, all 700 trillion kilograms of it, compressed into a sphere roughly 24 kilometers across. That is roughly the diameter of a medium-sized city. Now fill that sphere with matter so dense that its protons and electrons have been crushed together into neutrons, packed as tightly as the nucleus of an atom. Cover the surface with a crust harder than any material on Earth. and set the whole thing spinning dozens or hundreds of times per second. This is a neutron star, and we observe thousands of them. A teaspoon of neutron star material transported to Earth's surface would weigh roughly 4 billion tons. The surface gravity is approximately 100 billion times Earth's, meaning that a marshmallow falling from 1 meter above the surface would impact with more energy than a nuclear warhead. The escape velocity from the surface exceeds half the speed of light. Time itself flows measurably slower at the surface than in free space. When spinning neutron stars align their powerful emission beams with Earth, we see them as pulsars, objects that flash radio waves and X-rays with a regularity that rivals the precision of atomic clocks. Some pulsars rotate 600 times per second, making them among the most rapidly spinning objects in the universe. The equatorial surface of such an object is moving at a significant fraction of light speed, yet the object remains intact, held together by gravity and the strength of neutron-degenerate matter. But within the population of neutron stars lurk objects that make ordinary pulsars seem mundane. Magnetas are neutron stars with magnetic field strengths approaching 1 trillion times Earth's magnetic field, values that approach the theoretical maximum allowed by quantum mechanics. The energy stored in a magnetar's magnetic field exceeds the rest mass energy of a small mountain. These fields are strong enough to alter the structure of the quantum vacuum itself. Light passing through the magnetosphere of a magnetar is split into separate polarizations by the field, an effect called vacuum birefringence, which has been directly observed and which exists nowhere else outside of theoretical physics textbooks. The fabric of empty space becomes, in effect, a crystal. When a magnetar's magnetic field suddenly destabilizes, a process analogous to an earthquake in the star's crystalline crust, the released energy can briefly exceed the luminosity of all the stars in the Milky Way combined. In December 2004, a magnetar flare originating 50,000 light-years away measurably disrupted Earth's ionosphere, not through any particle beam, not through physical impact, but purely through the force of its radiation crossing the length of the galaxy. No human technology has ever approached magnetic field strengths within many orders of magnitude of what magnetars casually maintain the standard candle Type P1, a supernovae. Not all stellar explosions are created equal. Some happen in pairs, a slow, calculated theft followed by a precise, unavoidable detonation that has helped us measure the size of the observable universe itself. White dwarfs are the remnants of stars like our own sun. After exhausting their nuclear fuel and shedding their outer layers, these stellar cores, dense, crystallized, cooling, no longer generate energy through fusion. They persist by electron degeneracy pressure, a quantum mechanical effect that prevents electrons from occupying the same quantum state and creates a resistance to compression that can hold a stellar mass in equilibrium. But a white dwarf in a binary system has a problem. If its companion star is close enough, the white dwarf's gravity can slowly draw hydrogen gas away from that companion. The stolen material accumulates on the white dwarf's surface, compressed by gravity into a shell that builds up over millions of years. When the white dwarf reaches a precise mass threshold, 1.4 times the mass of our Sun, a value known as the Chandrasekhar limit, electron degeneracy pressure can no longer resist gravity. Compression begins. That compression heats the core. That heat triggers thermonuclear runaway. Within seconds, a detonation wave propagates through the entire stellar remnant at thousands of kilometers per second, fusing carbon and oxygen into nickel and iron in a single devastating event. The entire star is vaporized. Not merely its outer layers, the entire object, core and all, converted into an expanding shell of radioactive debris. What makes this explosion scientifically invaluable is its consistency. Because every Type 1, a supernova, involves the same critical mass reaching the same threshold and triggering the same nuclear reactions, they all release almost exactly the same amount of energy. They are, in the language of cosmology, standard candles, objects whose intrinsic brightness is known so that their observed brightness reveals their distance. This is the mechanism that revealed the accelerating expansion of the universe. By measuring type 1 as supernovae in distant galaxies and comparing their observed brightness to their predicted brightness, astronomers discovered that the universe's expansion was faster than expected, and getting faster. Dark energy was discovered by a white dwarf dying precisely. The explosion also distributes treasure across the cosmos. The calcium in your skeleton, the iron your red blood cells carry, the nickel found in stainless steel. These elements were forged in the thermonuclear death of white dwarfs billions of years ago. You are, in a very real chemical sense, the product of stellar theft and nuclear detonation. The universe spent billions of years building the ingredients necessary for you to exist. The golden collision. Neutron star mergers. Two dead stars are spiraling toward each other. They have been doing so for millions of years, locked in a gravitational orbit that bleeds energy through a mechanism Einstein predicted, but never lived to see confirmed: gravitational waves. These waves are ripples in the fabric of spacetime itself, not vibrations passing through space, but distortions of the geometric structure of reality, propagating outward at light speed. As the two neutron stars orbit each other, they continuously radiate these waves, losing energy with each revolution and spiraling closer as a result. The process is relentless and mathematically inevitable. Eventually the two objects will make contact. In the final minutes before collision, the orbital period shrinks from hours to minutes to seconds. In the last second, the stars complete hundreds of orbits. The gravitational waves they emit during this final plunge carry more power than the simultaneous light, output of all the stars in the observable universe. In September 2017, detectors on Earth picked up the signature of one such event: gravitational waves from a neutron star merger that occurred 130 million light-years away, followed 17 seconds later by a burst of gamma radiation. When the stars finally touch, the collision creates a fireball of conditions that exist nowhere else in the universe. Temperatures reach billions of degrees. Densities climb past nuclear density. Neutrons rain down on atomic nuclei faster than those nuclei can shed them, forcing the creation of increasingly massive neutron-rich isotopes. This process, rapid neutron capture, synthesizes elements that simply cannot be built in a stellar core or in a supernova. Gold, platinum, uranium, the heavy elements that represent the upper end of the periodic table. The collision ejects this material at speeds approaching 1/3 the speed of light. In the days following the merger, the radioactive decay of these freshly created nuclei powers a glow called a kilonova, an explosion that shines at peak with the light of several 100 million suns. Astronomers observing the 2017 event were able to spectroscopically identify the signatures of gold and strontium in this glow. A single neutron star merger produces gold in quantities comparable to several Earth masses. Every gold ring, every piece of golden jewellery, every gold coin ever minted carries atoms that were forged in a collision between two dead stars somewhere in the universe's history. The universe did not make gold in its birth. It made it in its deaths. The beginning of everything. The Big Bang travelled backward through time, past the formation of the first stars, past the creation of the first atoms, past the moment when the universe became transparent to light and the cosmic microwave background was born. Keep going, back through the first minutes when protons and neutrons were assembling into the first nuclei, back through the first second when quarks were condensing out of a primordial sea of energy. Go all the way back to the beginning. What we call the Big Bang was not an explosion within pre-existing space. There was no pre-existing space. The Big Bang was an event in which space itself, along with time, matter, energy, and the laws of physics, came into existence from a state we cannot describe with any physical theory currently available. The singularity that represents time zero is not a place or a moment in the conventional sense. It is the boundary of our ability to extrapolate physics backward in the first fraction of a second, a period shorter than any unit of time you have a word for. The temperature of the universe exceeded 10 trillion degrees. The four forces of nature were unified into a single interaction. Quarks had not yet condensed into protons. Protons had not yet condensed into nuclei. The entire observable universe, which today spans 46 billion light-years in every direction, occupied a volume incomprehensibly smaller than a single proton. As this primordial fireball expanded and cooled, the forces separated in a sequence of phase transitions. Gravity split off first. The strong force followed. Electromagnetism and the weak force decoupled last, around 100 picoseconds after the beginning. Each transition released enormous amounts of energy and permanently altered the structure of physical law. The universe we inhabit today, with its four distinct forces and its periodic table of stable elements, is the frozen residue of those transitions. By the end of the first 3 minutes, nuclear physics had done most of its foundational work. The universe contained roughly 3/4 hydrogen and 1/4 helium by mass, with trace amounts of lithium and deuterium. Every heavier element that exists today was forged later in stars. The Big Bang itself produced only the simplest building blocks. For the next 380,000 years, the universe remained opaque, a hot, dense plasma through which light could not travel freely. Then the temperature dropped below about 3,000 degrees. Electrons combined with nuclei to form neutral atoms for the first time, and the universe became transparent. The light that was freed in that moment is still travelling through the universe today, cooled by expansion into microwave radiation, filling the sky in every direction with a temperature of just 2.7 degrees above absolute zero. It is the faintest possible echo of creation, and it is one of the most important observations in all of science. Faster than light, cosmic inflation. Even the Big Bang, however, does not explain everything. The universe we observe has properties that cannot be accounted for by the simple expansion of a hot fireball. The cosmos is too smooth, too uniform, too geometrically flat. The extreme uniformity of the cosmic microwave background, which varies in temperature by only 1 part in 100,000 across the entire sky, requires an explanation that standard Big Bang cosmology cannot provide on its own. The leading solution is cosmic inflation, a brief period, occurring within the first tiny fraction of a second after the beginning, during which the universe expanded at an exponential rate far exceeding the speed of light. This does not violate relativity. Nothing was moving through space faster than light. Rather, space itself was expanding faster than light, carrying matter and energy along with it. The distinction matters because relativity constrains the motion of objects within space, not the expansion of space itself. The expansion during inflation was staggering. In an interval of approximately 10 to the negative 35 seconds, a period so brief it defies any attempt at intuitive comparison, the observable universe grew by a factor of at least 10 to the 26th power. A single quantum fluctuation the size of a proton became in that instant a volume larger than a grapefruit. The universe we inhabit today, spanning 46 billion light-years, grew from that grapefruit-sized region. This expansion solved the uniformity problem by ensuring that the entire observable universe grew from a region that was in causal contact, in communication, before inflation began. All the distant corners of the sky that appear identical in the microwave background were once the same point. But inflation did something else, something perhaps more consequential. The quantum fluctuations in the energy field driving inflation, random, microscopic, unavoidable by the rules of quantum mechanics, were stretched to macroscopic scale by the expansion. These fluctuations became the seeds of all cosmic structure. Every galaxy cluster Every great wall and cosmic void that exists today traces its origin to a random quantum wobble that occurred when the universe was less than a single proton in size. You and everything you've ever seen or touched are the descendants of quantum uncertainty. Some versions of inflationary cosmology predict that inflation did not end everywhere at once. In regions where the inflaton field, the energy source driving the expansion, happened to be in a high-energy state, inflation could continue indefinitely, eternally generating new regions of space-time that bubble off into independent universes. In this picture, our cosmos is one of an infinite number of expanding domains, each potentially harboring different physical laws and different fundamental constants. This is the multiverse, but we will return to it. Death of a Colossus. Hypernovae. Return to the present era, to the universe we can observe directly, and find the most extreme class of stellar death that current physics can fully account for. A star 50 times the mass of our Sun has spent 3 million years burning through nuclear fuel at a rate that would exhaust our own Sun in a geological eye blink. Its core has progressed through hydrogen, helium, carbon, oxygen, and silicon fusion in sequence, each fuel burning faster than the last, until the core is a ball of iron, the endpoint of nuclear fusion, the element beyond which no energy can be released by fusing further. The iron core grows. When it exceeds about 1.4 solar masses, it collapses. For an ordinary massive star, this collapse triggers a conventional core collapse supernova, an explosion releasing roughly 10 to the 44 joules of energy, the most powerful events in the universe on a per-event basis among ordinary stellar deaths. But this is not an ordinary star. It is spinning rapidly, and that changes everything. The conservation of angular momentum means that as the core collapses from Earth-sized to city-sized, its rotation rate increases by a factor of billions. The newborn neutron star or black hole at the centre spins hundreds of times per second. The infalling material cannot fall symmetrically into a rotating object. Instead, it forms a disk. The magnetic fields, already enormous in the parent star, are amplified to magnetar levels by the collapse and the rapid rotation. The result is a cosmic dynamo of extraordinary power. The energy stored in the spinning disk and amplified magnetic fields is released in jets that bore through the collapsing stellar material at near-light speed, emerging as gamma-ray bursts while simultaneously driving shockwaves of extreme violence back into the stellar interior. Layer after layer of the star is processed through temperatures and densities that briefly rival those inside neutron stars. Nuclear burning runs away across the entire stellar volume in seconds. The explosion that results, a hypernova, releases 10 to 100 times more energy than a conventional supernova. It synthesizes heavier elements in larger quantities than any ordinary stellar death can manage. The radioactive nickel produced powers an afterglow that can be detected weeks later from the other side of the observable universe. In the early universe, when stars were more massive and more plentiful than today, hypernovae may have been responsible for distributing the heavy elements necessary for planetary formation and ultimately for life. Every time you touch a piece of iron or breathe oxygen, elements that exist because stars died, you are touching the inheritance of a hypernova, titans of the large scale. Colliding galaxy clusters step back further still, far enough that individual stars are invisible, individual galaxies are dots of light, and the structures that fill your field of view are the largest gravitationally bound objects in the universe. Galaxy clusters contain hundreds to thousands of individual galaxies held together by the gravity of their combined mass, which is dominated not by the galaxies themselves, but by invisible dark matter and by the vast hot gas that fills the space between galaxies. A large cluster can contain the equivalent of 1,000 trillion solar masses of material spread across a region 10 million light-years across. When two such clusters approach each other, drawn together over billions of years by mutual gravitational attraction, The collision that follows is the most energetic event in the post-Big Bang universe. The dark matter in each cluster is largely transparent to itself. It passes through the collision region, deflected only by gravity, emerging on the other side in a pattern that astronomers have used as direct evidence for dark matter's existence. The galaxies within the clusters are sparse enough that they too pass through largely intact, though their shapes are distorted by tidal forces. The hot gas is another matter entirely. The intra-cluster medium, plasma heated to tens of millions of degrees, glowing in X-rays, is collisional. When two gas clouds moving at several thousand kilometers per second interpenetrate, they generate shock waves of extraordinary violence. The gas is heated to 100 million degrees or more, briefly making it the hottest large-scale object in the universe. X-ray observatories can observe these shocks in vivid detail, tracing the geometry of the collision billions of years after the event began. The most famous example, the bullet cluster, observed in detail since the early 2000s, shows the separated gas and dark matter, components so clearly that it remains one of the most compelling observational demonstrations of dark matter in astrophysics. The gas has been slowed by the collision and sits between the two clusters. The dark matter, unimpeded, has passed straight through and lies ahead of the gas. The mass distribution as measured by gravitational lensing follows the dark matter, not the visible gas. The shock waves generated in these collisions can accelerate electrons to near light speed across regions spanning millions of light years, producing halos of diffuse radio emission around the collision site that glow across the sky. These radio relics, as astronomers call them, are some of the largest coherent structures visible in the universe, and they are powered entirely by the violence of two enormous masses crashing together. The last catastrophe. Vacuum decay. Everything we have explored so far, even galaxy cluster collisions, even the Big Bang itself, takes place within a universe whose fundamental laws remain constant. The strength of the strong force does not change. The mass of the electron is the same today as it was a billion years ago. The rules of physics, however extreme the phenomena they permit, remain the rules. There is a scenario in which even this bedrock stability might be temporary. The Higgs field permeates every point in space. It is this field's interaction with particles that gives them their mass. Without the Higgs field, electrons and quarks would be massless and could not form atoms. The Higgs field has a particular energy value, and current measurements suggest that this value may sit in what physicists call a metastable state, not in the absolute lowest possible energy configuration, but in a local minimum that appears stable in the short term but could, in principle, quantum mechanically tunnel to a lower energy state. Think of it as a ball sitting in a shallow bowl on the side of a hill. The ball appears stable, small perturbations return it to the bottom of the bowl, but the true lowest position would be at the bottom of the hill, much lower. If the ball somehow tunneled through the walls of the bowl, it would roll down to a fundamentally different and lower state. If the Higgs field were to undergo this transition anywhere in the universe, the result would be an expanding bubble of true vacuum propagating outward in all directions at exactly the speed of light. The interior of this bubble would have different fundamental constants. The electron might have a different mass. The strong force might have different properties. Chemistry and nuclear physics as we know them would be impossible. The wave would be undetectable and unpreventable. Moving at light speed, it would arrive without warning. The light announcing its approach would arrive simultaneously with the wave itself. There would be no survival, no evacuation, no preparation. Every particle of matter encountered by the bubble wall would be converted to a configuration incompatible with atoms, molecules, biology, or any structure more complex than elementary particles governed by alien physics. Current calculations place the Higgs field in a region of parameter space that is described as metastable, stable enough to have persisted for 13.8 billion years, but potentially vulnerable over vastly longer timescales. Whether this represents a true existential risk or an artifact of incomplete calculations in a physically correct but ultimately stable field configuration is not yet known. Vacuum decay is not a prediction, it is a possibility, one that current physics cannot fully rule out, and it represents a form of power that transcends any explosion, any black hole, any cosmic collision, the power to rewrite reality from the inside out without leaving a single trace that it had ever been different. Relics of creation. Primordial black holes. In the first fractions of a second after the Big Bang, the universe was extraordinarily dense and extraordinarily hot. The distribution of this density was not perfectly uniform. Quantum fluctuations meant that some regions were slightly denser than others. In most cases, these overdensities were smoothed out by the rapid expansion and by radiation pressure. But in some cases, if the overdensity was large enough, the region collapsed directly into a black hole before any star had formed, before any galaxy had assembled. These are primordial black holes, and they are among the most theoretically versatile objects in cosmology. Unlike stellar black holes, which form with roughly a few tens of solar masses, primordial black holes could have formed with virtually any mass. Depending on when during the early universe they formed, they could range from objects with the mass of a paperclip to objects with the mass of 10,000 solar masses or more. The smaller ones in particular are quantum objects, tiny enough that the principles of quantum mechanics fundamentally govern their behavior. Stephen Hawking showed in 1974 that black holes are not perfectly black. Near the event horizon, quantum effects cause pairs of virtual particles to be separated, one partner falling inward past the horizon, the other escaping into space. The escaped particle carries away energy, and the black hole slowly loses mass through this process. For large black holes, the effect is negligible. Hawking radiation from a solar mass black hole is at a temperature less than a billionth of a degree above absolute zero. But for small primordial black holes, the process is dramatically faster. A primordial black hole with the mass of a large asteroid would, according to Hawking's calculations, be in the final stages of evaporation today, after 13.8 billion years of slow decay. Its final second of existence would release more energy than our Sun emits in a full year, in a burst of gamma rays, neutrinos, and exotic particles. No such burst has been definitively detected, but the search continues, and the potential payoff is extraordinary. Primordial black holes in the right mass range could account for some or all of the universe's dark matter. Massive primordial black holes in the early universe could have served as seeds for the supermassive black holes we observe today at the centres of galaxies, solving one of astronomy's most pressing puzzles about how those objects grew so large so quickly. They represent a direct window into the conditions of the universe's first second, a relic population that has been travelling through cosmic time since the beginning, carrying information about physics at energies we will never replicate in a laboratory. Scars in spacetime, cosmic strings. In the physics of the very early universe, as the unified forces separated into their distinct identities during a sequence of phase transitions, there was no guarantee that these transitions completed uniformly everywhere. Just as water freezing into ice can form regions with different crystal orientations, separated by boundaries called grain boundaries, the cooling universe may have formed boundaries between regions of space-time that settled into slightly different configurations. These boundaries, if they exist, are called cosmic strings. They are one-dimensional topological defects, objects that have length but no meaningful width or height. They are, in the most literal sense, infinitely thin lines of energy threading through the fabric of space. A cosmic string 1 meter long would contain the rest mass energy equivalent of a mountain. A string stretching from Earth to the Moon would harbour energy equivalent to the entire mass of Jupiter. Yet this energy is concentrated in a line that has no measurable width, narrower than any particle in the Standard Model by an enormous factor. As cosmic strings move through space, they disturb the space-time geometry around them, generating gravitational waves with a spectrum distinct from any other astrophysical source. Pulsar timing arrays, networks of precisely timed pulsars spread across the galaxy, used as a cosmic ruler sensitive to gravitational wave backgrounds, may already be seeing hints of this signal in their data. If confirmed, it would represent the first direct detection of physics from the universe's first microsecond. When two cosmic strings intersect, they can exchange partners and form closed loops. These loops vibrate like cosmic guitar strings, radiating gravitational waves and slowly shrinking as they lose energy. The spectrum of these gravitational waves carries a precise mathematical signature, one that future gravitational wave detectors may be able to identify and attribute unambiguously to cosmic strings. Some theoretical frameworks predict that cosmic strings could also serve as seeds for galaxy formation, providing the density perturbations around which matter clusters. This scenario is disfavored by current data, but it's not ruled out. Cosmic strings may thread the universe at low enough density to have escaped detection so far, while still contributing subtle signatures that future surveys will reveal. The invisible war, dark matter, annihilation. The universe contains 5 times more dark matter than ordinary matter. This invisible substance shaped the formation of every galaxy and galaxy cluster, providing the gravitational scaffolding around which visible matter assembled. And yet, despite decades of searching, we do not know what dark matter is. One of the leading candidate classes, weakly interacting massive particles or WIMPs, would have a remarkable property. If the dark matter particle is its own antiparticle, then when two dark matter particles collide, they annihilate entirely, converting their combined rest mass into pure energy, according to Einstein's equation. 1 kilogram of dark matter annihilating with 1 kilogram of anti-dark matter would release energy equivalent to approximately 40 megatons of TNT. No other process extracts energy from matter with such absolute completeness. In the dense cores of galaxies and galaxy clusters where dark matter concentrations are highest, the rate of such annihilations could potentially be detectable. The annihilation of WIMP mass particles would produce gamma rays at specific energies, a spectral line that would be unmistakable against the broad continuum backgrounds of normal astrophysical emission. Space telescopes have been searching for this signal for over a decade. Near the extreme density environments around black holes, dark matter densities can reach levels where annihilation rates become significant. Some theoretical models predict spikes of dark matter density near black hole event horizons, which could produce detectable gamma-ray or neutrino signals. Observing these signals would simultaneously confirm the particle nature of dark matter and map its distribution in the most extreme environments in the universe. The absence of a clear detection so far has constrained but not eliminated the WIMP hypothesis. It has pushed the allowed parameter space toward heavier particles, weaker couplings or lower densities, but it has not solved the mystery. Dark matter remains one of the largest and most consequential gaps in our understanding of physical reality. If it does annihilate, and if we eventually detect that annihilation, the discovery would be among the most significant in the history of physics, comparable in magnitude to the discovery of nuclear fission or the confirmation of gravitational waves. Nature's particle, accelerators, ultra-high energy cosmic rays. Somewhere in the universe, particles are being accelerated to energies our most advanced technology cannot approach. Individual protons accelerated to 99.9999% of the speed of light arrive at Earth carrying macroscopic amounts of kinetic energy. Energies equivalent to a baseball thrown at 60 miles per hour, compressed into a single subatomic particle. When one of these ultra-high energy cosmic rays strikes Earth's atmosphere, it triggers an air shower, a cascade of secondary particles that fans out across hundreds of square kilometers of ground. The cosmic ray particle collides with an atmospheric nucleus and produces hundreds of new particles, each of which collides with other particles, which produce more particles, until the shower front, moving downward at nearly light speed, contains billions of particles spread across an area the size of a major city. The Pierre Auger Observatory in Argentina covers 3,000 square kilometers of detectors precisely to catch these rare, enormous air showers. At the highest energies, the flux of cosmic rays is so low that even Auger detects only a handful of events per year. What accelerates these particles? This remains genuinely unresolved. Supernova shock waves can accelerate particles through a process called diffusive shock acceleration. Particles bounce back and forth across the shock front, gaining energy with each crossing. But this process runs out of steam below the most extreme cosmic ray energies. Something else must be responsible. The most likely candidates are the jets of active galactic nuclei. Stretching millions of light years, threaded with powerful magnetic fields, carrying plasma at near-light speed, these jets are the largest natural particle accelerators in existence. A particle trapped in the magnetic field of a relativistic jet for even a fraction of its traversal time could, in principle, gain energies matching the observed cosmic ray maximum. At the very highest energies, protons travelling through the universe interact with the cosmic microwave background radiation, the faint echo of the Big Bang that fills all of space. These interactions limit how far such particles can travel before losing energy, meaning that the most extreme cosmic rays must originate relatively nearby, within a few hundred million light years. This constraint, known as the GZK limit for its three predictors, means the sources of the most powerful natural particle accelerators in the universe are, cosmically speaking, in our neighbourhood. We simply have not yet identified them with certainty. The energy of nothing, quantum vacuum fluctuations. We arrive, finally, at the most counterintuitive entry in this catalogue of cosmic extremes, a force that operates not in the hearts of dying stars or at the edges of black holes, but in the supposedly empty space between atoms, in the vacuum between planets, in the void between galaxies. Quantum mechanics prohibits true emptiness. The uncertainty principle, which constrains how precisely certain pairs of physical quantities can be simultaneously known, applies to energy and time. This means that the energy of a given region of space cannot be precisely zero for any finite duration. Instead, the vacuum seethes with quantum fluctuations. Pairs of virtual particles that borrow energy from the vacuum exist briefly and then annihilate each other before quantum mechanics can register the violation. These fluctuations are not hypothetical, they are directly measurable. The Casimir effect demonstrates that two closely spaced parallel metal plates in a vacuum experience a measurable attractive force, because the space between them excludes some wavelengths of virtual photons, creating a slight imbalance in vacuum energy pressure between the inside and outside of the gap. Precision measurements of this effect agree with quantum theory to extraordinary accuracy. Hawking radiation, the slow evaporation of black holes, can be understood as a vacuum effect. Near the event horizon, virtual particle pairs are created as always, but now one partner can fall inward past the horizon while the other escapes. The escaping particle becomes real, carrying away energy that the black hole must supply. Over enormous spans of time, this process drains even the most massive black holes of their energy and mass. The cosmological constant problem is the most dramatic manifestation of vacuum energy's strangeness. Quantum field theory predicts a vacuum energy density roughly 10 to the 120 times larger than the cosmological constant actually observed. This discrepancy, 120 orders of magnitude, is the largest known disagreement between a theoretical prediction and an experimental measurement in all of physics. Some cancellation mechanism reduces the predicted vacuum energy to match observation, but no one knows what it is. Despite this mystery, quantum vacuum fluctuations are not merely a curiosity. They seeded the density fluctuations that inflation stretched to cosmic scales. They drive the eventual evaporation of black holes. They may be connected to the dark energy accelerating cosmic expansion. The energy of nothing may turn out to be one of the most important energies of all. Beyond the horizon, the multiverse. Every phenomenon we have examined tonight, every explosion, every collision, every extreme, has occurred within the observable universe, the sphere of space, 46 billion light-years in radius, from which light has had time to reach us since the Big Bang. This is our cosmic horizon. Beyond it, space continues, and under eternal inflation, it may continue forever, generating new domains of spacetime continuously, each with its own physical history. In the framework of eternal inflation, our Big Bang was a local event. The inflaton field, which drove the exponential expansion, reached a low-energy state in our region of space, and inflation ended here, producing the hot, dense fireball we call the Big Bang. But in adjacent regions, vastly distant beyond any possible observation, the inflaton field remained in a high-energy state, and inflation continued. New low-energy regions have been nucleating continuously, each becoming an expanding universe with its own matter, stars, and potentially its own version of the physical constants. In some versions of this picture, the fundamental constants of nature, the strength of gravity, the mass of the electron, the speed of light, are not fixed by any deep theoretical necessity, but are instead determined by the local configuration of quantum fields at the moment inflation ended in each bubble. Different bubbles produce different constants. Most configurations produce sterile universes in which atoms cannot form, stars cannot ignite, and complexity cannot emerge. A small fraction produce universes like ours. This is not a comfortable picture for physics. A theory that predicts infinitely many universes with different laws is, in the conventional sense, nearly impossible to test. You cannot falsify a prediction about regions you can never observe. Some physicists embrace this as the natural consequence of the mathematics. Others argue that a truly scientific theory must make testable predictions, and that an untestable multiverse, however mathematically consistent, lies outside the boundaries of science. What makes the multiverse relevant to tonight's journey is scale. Every force we have contemplated, the strong nuclear force, gamma-ray bursts, vacuum decay, the Big Bang itself, occurs within one universe, one solution to one set of physical equations. The multiverse, if it exists, represents the totality of all possible solutions, an infinite ensemble of realities, some harbouring beings capable of asking these questions, most harbouring nothing at all. The total energy of an infinite multiverse is, by definition, infinite. Every configuration of matter and physics that mathematics permits exists somewhere within it. Every history is realised. Every possible end is reached. The multiverse is not the most powerful force in any single universe. It is something beyond that, the space of all possible forces of nature, all possible instances of the question we have spent this evening asking, what we are. We have travelled far tonight, from the interior of atomic nuclei, across the raging accretion disks of quasars, through the gravitational death spirals of neutron stars, and out to the theoretical edge of all possible existence. We have visited forces that operate at every scale nature permits, from femtometers to billions of light-years, and examined phenomena whose energetics challenge every intuition we carry from daily life. What is the most powerful force in the universe? Perhaps the honest answer is that the question itself is too small. Power in the cosmos does not reside in any single phenomenon. It is distributed through an intricate hierarchy. The strong force commanding the interior of nuclei, electromagnetism shaping chemistry and light, gravity organising matter on every scale above the atomic, dark energy dictating the ultimate fate of everything. These forces do not compete, they compose. The universe is not a single instrument playing a single note, it is an orchestra, and every note played at every scale is part of the same piece. But there is a quieter truth underneath all of this. Every force we have examined, Every explosion and collision and phase transition ultimately conspired to produce the conditions necessary for complex chemistry, for planetary surfaces, for liquid water, for the emergence of life. The calcium inside your bones was forged inside a white dwarf before being scattered by a thermonuclear detonation. The iron in your blood was synthesized in the core of a star that exploded billions of years before Earth existed. The gold in any jewellery you've ever worn was created in the collision of two neutron stars, flung across space at 1/3 the speed of light. You're not made of ordinary matter, you're made of extraordinary matter, the output of billions of years of stellar nucleosynthesis, distributed across the galaxy by explosions, gathered by gravity into a planet, assembled by chemistry into life, and organised by evolution into a mind capable of asking where all of this came from. The universe has been running for 13.8 billion years. It has survived phase transitions, gamma-ray bursts, and the slow, relentless pressure of dark energy. It has assembled hydrogen atoms into everything you have ever seen. And at some point along the way, it produced beings who could look up at the night sky, recognize those lights as other suns, and understand, however imperfectly, the forces responsible for their existence. That may be the most astonishing thing in this entire catalogue. Not a black hole, not a gamma-ray burst, not vacuum decay, or the Big Bang. The most astonishing thing is that matter became aware of itself. The universe looked at its own reflection and asked, "What am I?" We are its answer. The strong force holds your atoms together as you read these words. The light from distant stars crosses billions of years to reach your eyes. Somewhere at the edge of the observable universe, a gamma-ray burst is unleashing energy beyond imagination, carrying no awareness that you exist to observe it. And yet you do observe it. You have names for it. You have equations describing it. You have the astonishing capacity to feel wonder about it. That capacity, wonder, inquiry, the drive to understand, may be the rarest and most extraordinary phenomenon the universe has yet produced. More rare than a magnetar, more unexpected than a quasar jet, more fragile than a neutron star crust, and infinitely more precious. The universe did not have to produce observers. The physical constants could have been slightly different, and atoms would never have formed. Stars might have burned out before planets could assemble. The window in which consciousness can exist is narrow and almost certainly finite. We live inside that window. We live at a moment in cosmic history when the stars still burn, the universe is still structured, and the information needed to understand our origins is still detectable across billions of light years. That window will eventually close. In the far future, as dark energy carries galaxies beyond the cosmic horizon, the evidence for the Big Bang will become undetectable. Future civilizations, if any exist, will inherit a universe that appears static and eternal, with no visible record of its violent origin. They will not be able to deduce what we have deduced. The window closes. We are here now, while it is still open, looking up, asking questions, answering them. Sleep well tonight beneath a sky full of light that has been travelling for billions of years to reach you. Every photon that reaches your eyes carries a story of stellar birth and death, of cosmic forces balanced in delicate tension, of a universe complex enough and curious enough to look at itself and ask what it is. You are the universe asking that question, and for now, that is enough.